Our next speaker is Mr. Ola Rignal. He is the Director of Flight Test and Verification of Aeronautics at the SAAB. He is responsible for all the military flight test activities regarding aircraft, airborne vehicles, including unmanned vehicles, unmanned systems. He is also the member of the board at the Linköping City Airport. He is a member and fellow of the Society of Experimental Test Pilots. But before joining the SAAB, he spent more than 10 years in the Swedish Air Force as an operational pilot. And probably that background experience helped him a lot to become an expert and become a director of the flight test and verification. He has participated in the Gripen program, and he also participated in a number of events in connection with the marketing of the Gripen, which includes flight operations across the globe. And before becoming the director of the flight test and verification, he was the chief test pilot for the military aircraft at SAAB from the year 1999 to 2004. He is going to talk about how the flight testing was carried out at the Gripen, which is the Carefree single-engine fighter aircraft similar to LCA. In fact, yesterday there was a lot of talk about the safety aspects. I'm sure you will also cover those aspects in his lecture.
Mr. Chairman, ladies and gentlemen, good morning to you all, and thank you for letting me present some of the thoughts and experiences of the Gripen test flight period. First of all, it's wonderful to be here because this gave me the opportunity to leave 1 meter of snow and minus 20 in the home city of Linköping, because this is much better, I guarantee. Today I will cover flight testing of the Gripen, a carefree single-engine fighter aircraft, and hopefully we'll get the picture back. And I will discuss from left to right in the picture that you see right now, the Gripen AB, the first version of the Gripen AB, the middle picture, the Gripen CD, plus the right picture, the EF, or the next generation Gripen, which is similar to the Gripen IN that we offer to India. But first, I will give you some videos. This is a situation you don't want to expose any operational pilot to, because this is an uncontrolled maneuver. Luckily enough, this is under a controlled test situation. This is when we did the spin trials with the Dash 2 aircraft a few years back. And I will now try to cover what we have done to avoid getting operational pilots into this kind of a situation. So why do you need a carefree fighter? Well, during operational sorties, of course, you want the pilot to be able to focus on his tactical objective. He shouldn't need to care about keeping restrictions and limitations of the aircraft. In the same way, during training, you don't want the pilot to use his energy to learn the basic performance of the aircraft. He should become a professional in delivering force into the target. Thirdly, he, of course, should have the confidence of the basic platform and the subsystems. You need to be confident in the fighter that you fly. And last but not least, the training needs to be cost-effective. The more sorties you can spend on tactical training, the better it is, instead of general handling of the aircraft. So, from a pilot's perspective, what is a carefree aircraft? Well, a reliable engine that works flawlessly. You need to be able to mishandle the engine within the operational envelope. You should be able to use brute force on the throttle no matter where you are in the fighter envelope. In the same way, the flight control system must keep the aircraft within the operational boundaries no matter the external stores, and that is what we call carefree. To do this, we have a system that we call MLL, Maximum Load Limiter, and I will get back to that later on. The pilot should also be able to not care about keeping within NC, alpha, or speed limits during flight. Everything should be automated, and you should be able to concentrate on your tactical scenario. And if for any reason the aircraft still encounters an uncontrolled situation, the flight control system should be able to take you back into the controllable envelope without you having to work for it. And of course, HMI solutions that are intuitive and easy to operate. So my agenda for the day is to give you some feedback of how we did the engine testing of the RM12 engine, which is a modified 404 for the Gripen AB and CD versions. I will also cover in some aspects the MLL testing of the flight control system, and I will then finish off with a high angle of attack and spin testing that we did. Starting with the fighter. Sweden is a fairly big country up north in Europe. We are surrounded by extremely cold water. We have a fairly large unpopulated land area where you don't want to land without being capable of getting back to civilization. Luckily, there are no sharks in the water. There are no tigers in the woods. But still, you have to be sure that you don't land, if you have a mishap, that you have to land somewhere where you can get back to civilization. So, the RM12 engine, which is the Swedish word, it is a General Electric 404 that we have modified to be able to rely on a single engine aircraft operation. First of all, we exchanged the fan to get the better airflow, but also to have a bird strike capability up to 2 pounds or 0.5 kilograms. We also increased the steel casing around the compressor, also to make sure that we could take a bird strike. We changed some parts of the combustor. We put in the low pressure turbine. We made it possible to do what we call the Tiger Start. It means that you can go from a cold aircraft to airborne within 90 seconds. And to be able to do that, you have to be able to take higher temperatures during the startup. And we also changed some of the blades into monocrystal blades. In the high pressure turbines, also monocrystal blades. The afterburner improved efficiency. And last but not least, we had to make sure that the control mechanisms of the engine were safe enough. So we had to duplicate some of the features that you see on this slide. Now, the Gripen operational envelope is, as you see on the slide, it's a fourth generation fighter aircraft and high G performance, Mach 2. And you can see on the right side of the slide that it's the operational performance of the General Electric 404. So this is what we got when we bought the engine, and we now needed to make sure that we could use the engine within this operational envelope. Some of the test activities that we did is shown on the slide, and I will cover two of them in a very top-level perspective. First of all, the water ingestion trials, which we combined with brake trials. We are in a climate zone in the northern part of Europe where there is a lot of rain. I think similar to what you have in India, even though we don't have the monsoons up the north. So we have to make sure that the engine can take a lot of water in there during landing and takeoffs. Of course, we also land on very slippery runways, especially during winter time. Braking action down to 0.1. So we also need to make sure that the brake works. So you have an anti-skid and anti-brake systems on all wheels, including the nose wheel. After doing the water ingestion trials, we carried on with several different engine trials, which I won't mention today, but I will go into what we did regarding relight during flight. This was the planned test points for relights during flight that we planned to do. Initially, we started out fairly low level, about 5,000 meters or 16,000 feet, fairly low speed. Then we increased the speed low level, and then was the plan to go further up. And in the end, we should do an APU-assisted restart, and in the end also windmilling, so we would let the aircraft go entirely cold, which is, from a pilot perspective, kind of an uneasy situation. Because then you have to rely on the backup system of the aircraft. You fly what we call dead stick. So to be able to prepare the aircraft, we had to start talking with our design people. We had to go into the subsystems and make sure that all the subsystems could cope with an engine failure during flight and then be able to restart without giving any additional failures to the aircraft. We also looked into some other important issues like adjusted weather minima, flight test instrumentation and theodolites and control rooms. We had to make sure that we had a dedicated test area. In Sweden, we have a large test area up north, but it's up north, and during winter time, it's almost dark 24/7. However, during the summertime, it's light 24/7 because you're above the polar circle. But we wanted to make sure that we had a test area close to our home base in the south part of Sweden. And of course, we also needed to have an emergency landing airfield for dead stick landings. Luckily enough, we are blessed with a lot of lakes in Sweden, and there are some really large lakes. So you see the lake in the left part of this picture. It's the Lake of Vättern. It's about 150 kilometers from north to south. And this is also a restricted area where we can do all kinds of trials. It's just about 40 kilometers from our base, which is in the center of the picture. So this is where we decided to go for the relight trials. Now, to be able to do it in a safe manner, we had one dedicated test aircraft, the Dash 4. It's a dedicated aircraft for engine and general system trials. It differs from the other test aircraft, or it did, because it's a retired aircraft. It had a high amount of analog instrumentation compared to the other test aircraft that we had. We also equipped the aircraft with extra batteries, NICAD batteries, and emergency hydraulic pumps as a backup if the ordinary hydraulic system didn't work. This was a heritage from the former fighter, the Viggen, that we had earlier on in the Air Force, and which I flew when I was an operational pilot. Now, we also did some preparations to the aircraft before flight. We put in a new APU software because during development we found that the software wasn't all up to the levels that we expected. We also changed the oil into the engine. We had to change the viscosity of the oil. We had to check the spark plugs, and you can then see the rest. One crucial thing was the charging of the batteries. We had a limitation that the batteries needed to be charged within the last 72 hours. And due to the weather in Sweden, once in a while you didn't get weather within 72 hours, and then you had to recharge the batteries, and then you were on hold again. Flight test training. We had a dedicated test team, individually assigned for the entire campaign. Of course, when we made simulated trials for restart training and emergency training, then we put the system simulator in connection with the Iron Bird and the control room to be able to train restart training and emergency training. And finally, we put the relay aircraft into the engine bay, connected the control room, and did crew training, mainly regarding critical failures of the engine or the systems. And last but not least, the pilots had to train themselves. So we put them on some preparation flights, and you can see roughly what the preparation flights consisted of. And all in all, this took quite a long time to prepare the aircraft for the engine trials. And then we came to the real test. This is a very simplified picture on how we did it, but we came up from the north part of the picture, and then on about 10,000 feet or 3,000 meters, we started up the APU. We then climbed up to 70,000 feet, where we then went back on thrust to make able to the engine to cool down. And then last, we cut back to flight idle, and then we shut down the engine. And I guarantee that the pilot that did this the first time, he was really on his toes when he cut down the engine, because it's not a normal thing to do from a pilot, at least while you're airborne. And hopefully, then the engine would relight. And luckily, it did. We were planning, as you saw earlier on, quite an amount of tests. Halfway through the program, our customer, the Swedish Air Force, decided that they had the data and the coverage that they needed. So we actually ended up with just doing the low-level test points when it came to hot restart or APU-assisted restart. And that's where the customer said, now we don't want to do more. It could be one of the reasons are that they are actually the owner of the test aircraft, so they don't want to risk it anymore. Nevertheless, the engine is very reliable. Since then, we have done some post-certification developments. We have put in a fader control system, also fan life improvements. We put also in radial flame holders, the same flame holders that you will find in the F-18EF, and also put in some measures to reduce the life cycle costs, and also making sure that the engine is worldwide climate adapted. So all in all, this gave us an engine that is, from our perspective, carefree. So now when you have the engine, you need to make sure that the flight control system is up to speed as well. So we put together a high angle of attack flight test program. Now the flight control system of the Gripen is a fully digital fly-by-wire system, 3 channels. You have what I call the maneuver and load limiter, the MLL. It means that you as a pilot, you can just yank the stick into the end position, and no matter where you are in the envelope, you will get maximum performance, either G, NC, or alpha. And you will never, ever be able to overstress the airframe. So that is the goal of the maximum load limiter. Within the flight control systems, we have different control laws. Within the green part, the region 1, this is the normal flight envelope of the aircraft, where the operational pilot will normally find himself. Region 2 is where, if for any reason the pilot would yank the aircraft, maybe going into wake turbulence or something, the auto-recovery system will take the aircraft back into the normal envelope. And then region 3, now we are talking in an uncontrolled situation, the pilot could let go of the stick. The aircraft will take itself back into the normal flight envelope. So you as a pilot, you should actually just release the stick, or at least go open loop on the stick. For flight test purposes, we also put in a flight test function where we can override the MLL system to get the aircraft into spin and high angle of attacks. So the objectives, of course, was to verify the MLL, but also to demonstrate recovery from stalls and spin, and define an operational min speed limit. The min speed limit right now is 100 knots, about 180 kilometers per hour. Later on, we added some test points, which you can see on the slide, but I won't go into them right now. Now, the test program was scheduled like this. We would initially do an interim MLL limit verification. I think this will answer some of the questions yesterday regarding IOC and FOC. And we would go through what you see on the left part of the slide and then deliver to the Air Force an IOC regarding MLL and high angle of attacks. Then we would go into the initial spin, the spin testing and the carefree testing, and by the year of 2000 deliver the full operational capability regarding MLL to the Swedish Air Force. So this was the plan. Now, when you do a flight envelope expansion, you need to address it in a safe manner. So, of course, we started out to looking at the flying qualities in the normal envelope, and then step by step, we went all the way up to supersonic MLL testing in the supersonic region. Before we did flight test, of course, we did desktop simulations and simulator trials. And then we used a test aircraft, the -2S test aircraft. Then we were supposed to verify the functionality, once again by simulator trials, and then using a production aircraft, fully instrumented, or actually an operational aircraft from a squadron. And if we found no departure, we would then clear the system for departure resistant to the operational squadrons of the Swedish Air Force. If we found any departure, of course, we would have to inflict some operational restrictions. Now, the store combinations of the Gripen, with all the external loads that you can put on the aircraft, you have roughly 2.4 million different alternatives. 75,000 of them would be fully realistic to expect on the aircraft. So how do you do this? Well, of course, you do what we call desktop simulations. We would put all the different data into desktop simulations, and they would run during night. Approximately 13,000 tests per load alternative. And they would then be visually graphed in what we call the thermo chart on the right side of the picture. And out of those, we would choose the most critical test points, roughly 25 to 30 of the most critical test points. Then we would go into the system simulator and shake them down further, and eventually you find yourself doing maybe 2 to 3 flights per configuration and doing approximately a total of 25 flights to clear the entire envelope of the aircraft. So, to do Carefree flight tests, you need a specifically modified test aircraft. You can see it on the slide. It's the Dash 2, new color scheme. Of course, anti-stall chute. It's mandatory when we do these kinds of trials. A special cockpit instrumentation and revised subsystems. And, of course, telemetry. It's a mandatory demand from us to have telemetry when we do flight tests. And this is how the aircraft looked inside. This is not the standard Gripen aircraft. The first version of the Gripen aircraft looked as on the left side with monochrome displays. Now you have full color displays in the CD and the NG version. But you can see they are for sure different. But it's very efficient when you do flight tests to have the right picture cockpit display. Before flight, we put the pilot into simulator training just before the flight. 1 hour before flight, he would do all the test points in a simulator, and then he would go out and do the real task. By doing so, he would be up to speed on all the different test points. And then, of course, during flight, we would, of course, use the results from the ground trials. We would dictate the criteria in angle of attack and angle of side slip for the pilot, but then we would run parallel simulation during the entire flight to be able to compare the real data from the fighter aircraft plus the data from the simulator model. And if they match, for sure, we can proceed with the next test point in a much quicker speed. The pilot, of course, has to assess the handling qualities during flight, and his analysis compared to the real-time analysis gave us the confidence to proceed with a high speed in the test program. So if we sum them up, this is for the AB version. You can see on the slide when we cleared different alternatives. You can also see in the yellow letters that we had to change the flight control systems to be able to cope with all the different external loads. This was not planned, but this is the outcome of flight test. You need to be able to change your system rapidly to be able to cope with a very tight test program. From a pilot's perspective, this is not fun to show, because this is to show you that you should do most of the tests in a desktop simulator. You should do very little test regarding flight test. And the reason for that is, of course, that you can verify your model, and you can then go back off the flight test and update the flow. And you can see in the lower part of the chart the cost for each test. It's much more efficient to do it in a desktop simulation. Flight testing is expensive. When it came to the CD version, we had a similar approach, and we cleared some of the about 50,000 stores combinations in the 2003 and 2004. And then eventually we also cleared the rest, about another 10,000 store combinations until 26. And the model concept is now used all over when it comes to external load certification and verification. So, last but not least, spin trials. Some aircraft, especially high performance aircraft, are capable of getting themselves into a spin situation for sure. We decided that we should show our customers that this aircraft is carefree. So we decided to proceed with spin tests. The final test strategy is as you see on the slide. We would do some anti-stall chute tests where we actually deploy the anti-stall chute during flight. We would then do aerodynamic verification and initial spin departure. And we would once again deliver an IOC regarding spins to the Swedish Air Force by the year of 1996, and the full operational clearance regarding auto-recovery mode by the year of 2000. I showed you the flight control systems earlier on. To be able to get the aircraft into a spin, we had to override the flight control system. So we integrated what we call the direct link mode, which you see in the center part of the slide. So by pressing a switch, we can actually yank the system over the limitations of the flight control system. And that is the only way to get the aircraft into a spin. So the setup for the entry to the post-stall situation was to come in low, high speed, then climb up, override the system, and then put the aircraft into a high angle of attack or spin situation. Hopefully, After post-stall, the aircraft would then return into a normal envelope. We started out with a single-seat test aircraft, the 39A, and you can see the test objectives down underneath. And I will now show you some videos from the A testing and some visualization as well. This is the first slide, and you can see before I start the visualization, you can see in the lower left part, you see the stick position. You can see up in the left corner some data. You can also see theta, phi, and alpha, and you can see the altitude in meters, which was the case when we started out this program. So let's see it. You can see how the afterburner is burning, and you can see how the pilot is yanking the stick to control the aircraft. And then he gets the aircraft into a stalled situation. A fairly benign test point, which immediately recovered, and you got back into the full operational envelope again. Then we proceeded towards a stall over the wing, and this is real footage. And now we can learn some Swedish as well. And you can see now that we are doing a tail slide, and during this tail slide we are also doing full throttle movements from max AB to flight idle and back to max AB again. And you can see how the aircraft recovers from the test point. Stall over the wing, once again visualized in the graphic system. And you see the blue and the red respectively, which is angle of attack and angle of side slip. And you can now see how the aircraft returns into the operational envelope again. And the same thing from the real theodolite footage.
Vi fortsätter rolla. Klart desorienterande. Nu kommer nosen ner. Jag släcker där. Vi går ur där. Vi får ett överslag uppåt. 35 grader.
And we're recovered once again. Now, when you do spin test, you want to have this real-time aerodynamic analysis. And I said earlier on that gave us confidence to proceed with the test. And this is how you compare. You overlay real data with the simulated trials. And if they match, you will proceed to the next test point, because then you can feel safe. Now, accomplished spin test for the A was roughly 150 spins or high angle of attack test points. We also then went to a production aircraft without the anti-stall chute, and we did some production verification as well, which was thrilling, I guarantee, because when you don't have the backup with the spin chute, it needs to work. And then, of course, we made dual seat spins as well. Sorry. Hold on. And this is the same setup from the dual seat. And you can see it's a very controlled situation, and the aircraft goes into the spin, and then the yaw rate starts to pick up. So, once again, we did a fair amount of test points for the dual seat, and overall, we found that we have now tried out spins and high angle of attack tests outside of the normal envelope. The green box in the middle of the lower right corner is the normal flight envelope of the Gripen aircraft. We have been all over the place. So now we think that the flight control system is fully verified. So all in all, three new flight control system software editions, and a total of about 230 spin test runs. And this was the final exam, ladies and gentlemen. Now the pilot is entering into a spin, and as soon as the aircraft is into a spin, he will let go of the stick. Watch his right hand while he's doing this. Sorry. You can see the hand down there. So it's open loop. And he sounds fairly calm, at least when it comes to breathing. and you see the aircraft recovers. So all in all, we actually verified the auto-recovery mode of the flight control system. Now, all the things that I mentioned so far is, of course, also included in the offer we do for India, the Gripen IM. We put together a demonstrator 2 years back, which incorporates, of course, new engines, the 414 engine, extended range, increased payload, and some tactical things, an AESA radar, and a MAV system. We did the flight test of this in 2 phases. The first phase concentrated on the new general systems, and like this, hopefully you see it. And then phase 2, we concentrate on the tactical systems. All in all, it went very well, and it gave us the confidence that May last year, we took the aircraft down to India for the Indian evaluation. And this is actually the same route that we flew down last Sunday with the 3 production aircraft to the Bangalore Air Show. And in India, we then did some hot weather trials up in Adampur and the Lee Air Force Base. And this was actually possible with the test aircraft. We had so much confidence in the test aircraft that we actually went over here. And just after returning back to Sweden, we went to the Farnborough Air Show. So all in all, the phase 1 and phase 2 flight test has compromised about almost 200 flights. My CEO yesterday wasn't quite sure about the amount, but almost 200 flights is accomplished. And we will continue now to do external stores tests, because now we have new stores for the aircraft, much more loads on the aircraft than before. This is the entire test program, and this is vital regarding the theme of this symposium. This is test flights with a fully instrumented test aircraft. We average about 400 to 500 test sorties per year overall. And you can see the waves of the program when it comes to for the initial AB verification, and then the CD verification, and now we will speed up with the next generation verification. When we do this, we will do it jointly, together with our customer. Historically, when we did the CD verification, we did a lot of flight tests, the red part. Our procurement agency did then their own flight test, and then the operational test unit of the Air Force did some tests. It's a lot of flight tests. We can't afford this in the future. So if we had taken the same methodology into the Gripen NG program, it would have looked like this. Now we have pressure on us from management to accomplish this. We will use the same test point for all 3 participants to cover their test purposes. So, ladies and gentlemen, summary and lessons learned. The Gripen fighter is carefree from a pilot's perspective, I guarantee. I can take any one of you up there and you will be able to fly it just with verbal comments from me in the back seat. When you do flight test and when you do design, challenge the can't be done mentality if you think you're right. You need to challenge the systems once in a while. For you design people out in the audience, involve flight tests from the beginning in the program. You have to be a professional in your field of expertise and stand up for your systems at all times. Consider that all delays in a program starts in the beginning of the program, and it's really hard to catch up in the end. For those of you who are flight testers out there, you have to be involved in the program from the beginning. If not invited, force yourself into the program, because you have some really vital experiences that you should integrate into the system. But listen to the design people's need. They are your customer. Remember that. You are not doing flight tests for your own purposes. You are doing it for the customer. And when needed, use the no vote. Say, we have to stop because this is not safe. This happened at several occasions during the programs I just showed you. And look for new technology and methodology and techniques outside your field of expertise. There are a lot of interesting technologies outside of the military complex that you can utilize within flight test, I guarantee. So with this, ladies and gentlemen, I would like to acknowledge some of my fellow colleagues back home who still are enjoying the snow. Some of my flight test engineers, my flight test manager, and one of the nowadays retired test pilots, Mr. Bernd Weimer. So with this, ladies and gentlemen, I thank you for your attention. And I invite you all to see us at the stand at the Lanka Air Force Base during their show, and we would gladly show you the latest, what we have in the simulators, and you will see the Gripen in the fighter displays. So are there any questions?
Back.
You emphasize the carefree handling of the aircraft.
Yes.
And you also showed a way of turning off the flight control system.
Yes.
By using the switch. Will an operational aircraft have that kind of control? And the reason I'm asking is that some aircraft today, some combat aircraft today, emphasize extreme maneuverability at the expense perhaps of many other factors. The Swedish Air Force Draken was the first aircraft, not well known, to do a Pugachev maneuver, which most people don't do now. Could you carry out those kinds of things, or have you deliberately chosen not to have that kind of capability because you think it's unnecessary or wasteful or dangerous or will reduce the life of the airframe or any such factors?
Okay, sir. The answer for your first question, no. The operational pilots will not have the possibility to override the flight control system. We don't think that they need it. And I think that partly answers your second question as well. No, we have decided together with our customers that we shouldn't have that capability. Of course, you could do it, just as you said, by letting go of some of the safety issues, and you can get even more tactical performance. But then you have to put a lot of emphasis on training on the aircraft to do that kind of a maneuver. That Draken maneuver that you mentioned resulted in quite a lot of crashes in the Swedish Air Force during the times. But it was a very effective maneuver at that stage.
Jabakumar, last question. We are running out of time. Already 30 minutes behind the schedule.
Yeah. The question is the alpha, you have the 26 degree alpha. Have you really flight tested at 28 degree alpha or higher than that using the spin recovery parachute and established that 26 is a safe alpha to recover?
We have been higher than 26 degrees of alpha during the angle of attack trials. We've been all the way up to, I think, 70 or 80 degrees angle of attack. But it's when we go into the post-stall or the stall region. But we wouldn't do any more flight tests than what we've done so far, if the customer doesn't want us to do otherwise. We would do anything that the customer would like us to do as long as we think it's safe, and they pay for it.
Okay. Thank you.
Thank you, Mr.
Thank you for your
Rignell.
attention, gentlemen and ladies.